So the integer and fractional quantum Hall physics in bilayer graphene is expected to be particularly rich because it has a multitude of inherent symmetries. Some of that we already saw in the previous nice presentation about tri-layer graphene. The reason is that the electrons have quite a number of different degrees of freedom. There's, of course, the spin degeneracy and the valley degeneracy that it shares with graphene's electrons. But in addition, in bilayer graphene, there's an unusual orbital degeneracy that is absent in conventional two-dimensional electron system. And you see that immediately when you write down the expression for the lambda level energy of the system. N here is the orbital index, and omega c is the cyclotron energy, which is determined by the effective mass, which is approximately 5% of the bare electron mass in bilayer graphene. And so you see here immediately that that there are two energies with lambda levels with 0 energy when the orbital index equals 0 and when the orbital index equals 1. And this is, of course, also reflected in the density of states in the presence of a perpendicular magnetic field. You have here this 0 energy bunch of density of states, which is double as large as for the other levels. It's also reflected in the whole conductance, of course. When you go from the whole side to the electron side of the discretized energy spectrum, you get a change in the whole conductance equal to 8 conductance quanta, rather than just 4 that you would expect from the spin and valley degeneracy. It turns out that the order in which these degeneracies are lifted is very important for the nature of the ground state that develops as you approach integer filling factors of these of this system, and it actually also will be important for fractional quantum Hall physics. And in order to illustrate that, I have a simple example here for you that actually comes from single layer graphene, but if you ignore the orbital degeneracy, it also holds for bilayer graphene. What I've done here is I've actually plotted lambda levels, how they behave as we approach the edge of the sample, and you can consider two extreme cases. The first case is when the spin splitting is dominating over all the other energy scales. And if you add then a valley splitting in addition, which is much smaller than the spin splitting, you end up with this diagram here. Notice that the levels with a different valley orientation, if you wish, that they bend in a different direction. One bends up and the other bends down. So if we now go to, if we put our chemical potential here, meaning that we are at filling factor 0, we call it, we are, of course, in a gap. We expect an incompressible integer quantum Hall state. And as we approach the edge, we actually we have two edge channels, but these edge channels are counter-propagating, and as a result, we have net current flow in the system. Compare this to the case where the valley splitting is larger than the spin splitting, then you end up with a diagram like this. It's very different here. The spin splitting is smaller than the valley splitting. If I again place my chemical potential here, I notice that as I go to the edge, there are no extended states crossing the chemical potential. And so this means that here we have a true insulator, whereas here we don't really have an insulator. We still have an incompressible state, but we have these extended states. And you see, there's a fundamental difference here. This has been studied to a great extent in a number of very nice papers. And the physics that I'm presenting here, I've oversimplified it a little bit. In reality, actually, we have a more complex phase diagram that is shown here for the case where we vary two parameters, the perpendicular magnetic field, and a second parameter, which is a displacement field. This is the field across two graphene layers, for instance. And you see here that, you know, if you go to a strong perpendicular magnetic field, you have a ferromagnetic phase. The spin splitting will be largest. Whereas if the displacement field is large, you're going to layer polarize. You're going to preferably place electrons in one particular layer. And for these lowest energy lambda levels at 0 energy, actually there's an intimate connection between the layer degree of freedom and the valley degree of freedom. Layer polarizing corresponds also to valley polarization. So this is just to illustrate you that this physics is more rich or richer than what we know, for instance, from our cherished gallium arsenide. And of course, if we add, in addition to that, the orbital degree of freedom and the fact that we have an orbital degeneracy for these zeroth energy states, then it becomes even more richer. It turns out that from experiment, we find that there's also an orbital splitting in the system, and this orbital splitting has important consequences, both for the integer quantum Hall physics as well for the fractional quantum Hall physics. You can immediately see here that particle symmetry is broken, right? Imagine that I'm filling only this level for electrons, then it's an n equals 0 level, whereas for holes, the first level that I would be filling is an n equals 1 level. That's different. And if I partially fill this, it's also going to have important consequences. The fractional quantum Hall states are, for instance, much stronger usually in an n equals 1 orbital level than in an n equals 1 level. We know that very well from the gallium arsenide case, and it's probably instrumental actually to take a look back and look what happens actually in gallium arsenide as we have a partial filling of lambda levels with a different orbital index. And that's highlighted here in this view graph that essentially shows the longitudinal resistivity as well as the Hall resistance for filling factors 1 all the way to filling factor 6. So it's not a magnetic field scale here, but a filling factor scale. So I'm covering partial filling of the lowest lambda level, of the second lambda level, as well as the third lambda level. And this graph nicely illustrates how the nature of the ground states that develop when we have partial filling of these levels with different orbital index changes dramatically. In the lowest lambda level, we observe fractional quantum Hall behavior, and all the fractions have odd denominators. This is our conventional these are our conventional Laughlin states, and this odd denominator fractional quantum Hall physics reigns supreme here in this lowest lambda level. If we move to the third lambda level, actually the fractional quantum Hall physics is conspicuously absent. We don't see fractional quantum Hall behavior anymore, and instead it has been superseded by charge density wave physics. Basically, the system now will break up into different geometric patterns of different integer filling factors. One example occurs at half filling of one of these levels, for instance, 9 halves and 11 halves. This so-called striped phase develops, where we have stripes of filling factor 5, for instance, in a sea of filling factor 4, and because there's an incompressible sea there because this is now anisotropic, it turns out that these stripes orient along a certain crystal direction, and this causes a strong anisotropy in the transport. The two curves that are shown here are for two different orientations of the current. And if we go away from half filling to quarter filling of one of these levels, actually we end up with something that looks very similar to a Wigner crystal. It's called a bubble phase, and the bubble contains more than 1 electrons. These bubbles, they reside in an incompressible sea of the adjacent integer quantum Hall state, and as a result, we get reentrant quantum Hall behavior. So very different from the physics here. Now, if we go to the second lambda level, we have a potpourri of everything. We have odd denominator fractional quantum Hall physics. We get these reentrant bubble phase physics. And in addition, a new physics appears at even denominator fractional fillings, 5 halves and 7 halves. It very much looks like the odd denominator fractional quantum Hall physics. You get a nice plateau in the Hall resistance, and in addition, the longitudinal resistance goes to 0. And this even denominator fractional quantum Hall physics is really unique to this second lambda level in gallium arsenide. And it tells you that the orbital index really plays an important role. And I would like to spend a few moments to why these even denominator fractional quantum Hall states actually occur in gallium arsenide in the n equals 1 level. Actually, if you boil it down to the essence, it really goes back to Pauli's exclusion principle. And in order to make this statement more tangible for you, let me do the following exercise. Let's consider integer quantum Hall state filling factor nu equals 1, which we can understand as a single particle effect. but we could, of course, also construct a many-particle wave function. And so if we choose our gauge appropriately, our basis functions look like this, z to the power m times an exponential. The exponential is boring and just tells us the spatial width of one of these states. And the important physics is actually in this front term here. Z represents the position of the electron in a complex representation. So x plus y, iy. So if we want to construct a many-particle wave function, all we have to do is make sure that it's antisymmetric. We can do that by taking the Slater determinant, and we end up with this simple form. We have this boring product of exponential factors, and then all the physics is contained really in this Jastrow P factor that tells us that this many-particle wave function has 0 at the location if we fix one electron coordinate at the location of all other particles. Now, a 0 in a wave function is, you can think, it has actually a similar effect as what a flux quantum will do, right? It expels the electron from that region, and we can sort of, at a hand-waving level, visualize this in this cartoon here, that there's an intimate connection between the location of the flux quanta and the electrons in the system. Now let's move to a fractional quantum Hall state. The most prominent one occurs at filling factor 1/3. In order to reach this state, we need to multiply our magnetic field by a factor of 3, or in other words, we need to add an additional number of flux quanta in our system equal to 2 times the number of electrons in our system. And for each of these extra flux quanta, we can add an additional 0 in our wave function. And of course, we should use the position of these zeros wisely in order to minimize the total energy of our system. So most generally, I could write it like this, and I need to somehow look for a good position to place these zeros. And what's the best way of doing it? Very obviously, I just put them exactly at the same place as my first set of zeros, namely where the other electrons are. And I end up with this wave function that actually was jotted down first by Laughlin and that won him the Nobel Prize. It really tells us that there are 3 zeros in this wave function at the location of every particle. One of them is to take care of Pauli's exclusion principle, and the other 2 are just to take care of Coulomb interaction. This is the way to minimize the Coulomb interaction energy. And pictorially, it corresponds, you don't see the flux quanta here very well, but having basically 3 flux quanta in the vicinity of each electron. And you now also immediately see from this way of approaching this problem that where composite fermions come from. And the composite fermions are this ingenious dodge where we basically form this compound particle where we have 1 electron and 2 flux quanta. And this compound particle then, by doing this transformation, it essentially amounts to screening the Coulomb interaction and to getting rid of this pair of zeros. And so we're left actually with the integer quantum Hall physics of compound particles. And this, for instance, filling factor nu equals 1 of these composite fermions corresponds to the fractional quantum Hall state at filling factor 1/3. Now, if we would spin this idea further to filling 1/2, for instance, this would obviously not work because we would get 2 zeros here, and the system would not be an antisymmetric wave function, and so we would not expect an incompressible ground state for this system. So how can we get even denominator fractional quantum Hall physics? Actually, there's 2 ways I know how to get fractional quantum Hall physics. The first one is the more trivial one. We can give our electron an additional degree of freedom by, for instance, having 2 filled subbands or by having a double layer system. In that case, due to this extra degree of freedom, we can again fulfill Pauli's exclusion principle. And indeed, you can come up with a many-particle wave function that now looks a little bit more complicated. You basically have 3 Jastrow prefactors, 2 of them containing only particle coordinates in either one of the layers, and then this interaction term describing interactions between the 2 layers. And this one anti-symmetrizes the wave function again, and you can get a fractional quantum Hall state. The second option electrons have is actually to pair up and mutate into bosons, because then, of course, we get rid of Pauli's exclusion principle altogether. But of course, pairing requires that we have some attractive interaction. And where would this attractive interaction come from in a system with so strong Coulomb repulsion? Well, it turns out that this composite fermion picture really gives an intuitive way of understanding where this comes from. As I pointed out to you, if we make this transformation to composite fermion, we are really screening the Coulomb interaction. Now, if we do the same transformation for lambda levels with higher orbital index, then we are also taking care of the Coulomb interaction, but because of the changes in the wave function, we are actually overdoing it. We are over-screening the Coulomb interaction, and the net result is an attractive interaction that may allow these composite fermions to pair up, Bose condense, and then give rise to something similar like superconductivity. And as a matter of fact, these even denominator fractional quantum Hall states that I showed you can really be thought of as a P-wave superconductor. P-wave because we are in a strong magnetic field and presumably all the spins are aligned, and therefore it has to be P-wave. Now, does this also happen in lambda levels with even higher orbital index? Well, it turns out it doesn't. The overscreening is so large that we have to question this picture of composite fermions altogether, and we don't see fractional quantum Hall physics anymore, or very, yeah. Okay, so that's basically the background I would like to provide to you regarding fractional quantum Hall physics, and in particular even denominator fractional quantum Hall physics, as it will play some role in the remainder for the experimental studies that I would like to show you on bilayer graphene. Okay. Now, so I hope that this introduction tells you that it's really interesting to have a system like bilayer graphene where you have this orbital degeneracy, where you can split this orbital degeneracy, and it turns out, as a matter of fact, that by having this displacement field, a field across the two graphene layers, that in principle what can happen is that the order of these levels changes. So it seems like a very cool playground for fractional quantum Hall physics, and it indeed is. And some reported results that I would briefly like to mention are shown here. This is some data by the Jacobi group, where they, actually it's not a conventional transport measurement, but rather is a measurement where they measure the derivative of the chemical potential with respect to the density. This is a quantity closely related to the so-called compressibility. And so, since integer quantum Hall state and fractional quantum Hall states are incompressible ground state, this compressibility is going to change drastically as we enter such a ground state. And it shows up here as a dark red region that is vertical, since we are plotting this on a filling factor axis. And when you look at this data, what you see is that you see all integer quantum Hall states at filling factor 0, -1, -2, +1, 2, 3, and 4. This essentially means that all degeneracies are lifted. The spin degeneracy, the valley degeneracy, as well as the orbital degeneracy. What you also notice here is that there is indeed fractional quantum Hall physics available, and the states that are observed here very nicely are 1, 2/3, 3/5, and 2/4. But you see that there's something strange here, because if we go from this lambda level to the next fully resolved lambda level, there is no fractional quantum Hall physics. Here there's again fractional quantum Hall physics. Here there's no fractional quantum Hall physics. That's actually the particle Hall symmetry that I was referring to. When I'm in this region here, I'm actually in a partially filled n=0 lambda level. Here, the fractional quantum Hall states are strong. If I move to this level, then I'm in this level, it's an n=1 level. And we know also from gallium arsenide that when you go to an n=1 level, actually the fractional quantum Hall states become weaker. And when I say weaker, it just means that the energy gap that is involved for excitations is substantially small. And that's reflected here. Then we go to this level here, we are again in an n=0 level, and sure enough, fractional quantum Hall physics pops up. It very nicely confirms this idea. Now, there was also a nice conventional transport experiment reported by the Alberto Morpurgo group from the University of Geneva. And it's a nice experiment because he observed for the first time in the context of graphene also even denominator fractional quantum Hall physics. It's not a particularly nice one, but you do have a strong dip, and as a matter of fact, there's also a nice sign of a plateau at filling factor -1/2. Now, if you look, filling factor -1/2 means that this lambda level is filled. It's an n=1 level. That's where we would expect, if we come from the gallium arsenide community, even denominator fractional quantum Hall physics. On the electron side of a sample, where you would be partially filling an n=0 level, he didn't see even denominator fractional quantum Hall physics. But unfortunately, in general, the quality on the electron and the Hall side the electron side was much worse in comparison to the Hall side. So it remained kind of open whether this is really confirming this idea that, you know, in order to have even denominator physics, you need an n=1 level. And as other work came up, actually things became more cluttered, and some fractional quantum Hall states were also clearly seen in this region here and so forth. And it motivated us to actually also look into this problem of fractional quantum Hall physics in bilayer graphene. And the main problem with bilayer graphene is that it's, of course, still substantially more disordered in comparison with gallium arsenide. But a few years ago, we actually came up with an interesting technique that allows us, even in a disordered system, to see quite a number of fractional quantum Hall states. And I need to spend some time to explain how this technique works, and I will illustrate it on single-layer graphene because their fractional quantum Hall physics is reasonably well understood. It goes as follows. So this is our device. It's at that time it was actually a graphene layer that was either directly sitting on silicon oxide or it was suspended. Here I'm showing data for a suspended device. And it's a two-terminal geometry, so I cannot show you the Hall resistance and the longitudinal resistance separately. You just get a single curve. And what you see here is basically integer quantum Hall physics. The plateaus are not very nice. It's a fairly disordered sample. And what you also notice here is that there are a large number of fluctuations on top of this, what I would call the background, even though it's the main signal that you're normally looking for. So, and actually when I showed this presentation to a number of experts in the graphene community, some of them told me, we have seen these fluctuations as well and we trashed the sample. That's actually a big mistake. It turns out that in these fluctuations there's a lot of interesting physics, and I would like to convince you about this. Now, in order to study these fluctuations, this background is really it's a nuisance, this background, and it turns out that there's a rather simple way to get rid of it, and so that you can really focus on the fluctuations only. And it's actually, these fluctuations are not really new. Similar physics was already observed in gallium arsenide, and some other people have reported these fluctuations in their samples, but they just didn't do anything with it. Okay, so what we do is the following. Instead of measuring the conventional conductance, we actually wiggle on the backgate, and by wiggling on the backgate, we generate, if we apply a DC voltage across our two terminals, an oscillating current as well. And we take a ratio of the amplitude of this oscillating current and this oscillating AC voltage to the backgate, and this is a quantity referred to as the transconductance. And this is the quantity that is plotted here, and we see here that our background has entirely vanished, and we end up with regions where we have very strong oscillations or spikes in the transconductance. Now you may say this is probably noise or universal conductance fluctuations or something like that, but it's certainly not if you look at this graph here, which is basically this transconductance plotted in a density versus magnetic field plane, and zero density corresponds to this point here, because what you see here is that these fluctuations are really reproducible as I systematically change my magnetic field. And something that might jump to your eye is that there are lines here, bundles of lines that all seem to run parallel. As a matter of fact, I can highlight this a little bit better by plotting these lines of key filling factors here. For instance, if you look at nu equals -2, you see that, and it's even far away from this slope of nu equals -2, that you get these parallel lines. Also, for filling factor nu equals 0, you see these lines, and you see even lines that are much steeper which actually suggests that these are following some fractional filling of the system. So, as a matter of fact, of course, many of these bundles of parallel lines you see with the naked eye, but here it becomes rather complex to distinguish the specific slopes that are available in this data. And there's actually a way to bring that out more clearly by doing an analysis of your data. And what we do is essentially the following. We construct what we call a correlation function. And this correlation function does the following. We take a certain analysis window in our data, and we have many data points within this window, and we take any pair of two data points, and we connect a line between these two data points. Now, if this line that we connect between these two data points follows the slope of the filling factor that we select, and I will call it here nu, then these pair of data points will contribute to we will make the product of the transconductance value, and it will contribute to the sum if indeed the slope corresponds to that particular filling factor. So what this correlation function will do is it will show a spike whenever there are lines following that selected filling factor. If in this data set I would take a filling factor that corresponds to this slope, I would expect that this correlation function is basically 0. Whereas if I would take this filling factor, I would expect a strong signal. And if you do that, you can represent it actually in a polar diagram where the angle just represents the slope in this graph. And if you do this for different analysis windows, you will indeed see that depending where you place your analysis window, you're going to get a peak in the signal. For instance, this is an analysis window taken probably around here, and you get a spike near nu equals 0. If you do that for a large set of windows, you actually can select here different fractional fillings. You can discover fractional fillings in these diagrams. So it seems as if we can extract from this set of data integer quantum Hall states as well as fractional quantum Hall states. As a matter of fact, it turns out that this transconductance method for detecting incompressible ground states was the first one to observe fractional quantum Hall physics in single layer graphene, prior to people starting to use these suspended flakes with current annealing, as well as these van der Waals heterostructures where they sandwich their single layer graphene between hexagonal boronite layers. Now, how can we understand these bundle of parallel lines? Well, it turns out that it is a signature of charge localization physics in the quantum Hall regime. And in order to explain that to you again, I need some background information. It turns out that these bundles of parallel lines had been observed before in experiments done in the Jacobi group at the time when he was still at the Weizmann Institute, and we were also involved there. And in this experiment essentially goes as follows. We have a single electron transistor that hovers above the sample, and the single electron transistor can be thought of as a very sensitive electrometer. It can measure the local chemical potential, and of course, if you wiggle the backgate, you can actually measure the derivative of the chemical potential with respect to the density, the compressibility. And so this is the compressibility plotted here in a magnetic field versus density plane, much the same way as I showed you my transconductance data. And it again has these bundles of parallel lines following one of the integer filling slopes where we expect an incompressible ground state. Now, where do these compressibility signals come from? Well, it comes from the following. Imagine that you have a system that is perfect, no disorder. Then if you add charges to the system, the charge is going to spread across the entire sample. And so basically the change in density or the change in backgate voltage required to add an additional charge is very small because it can spread over such a large space. And as a result, the chemical potential is going to up very smoothly because of the finite density of states. Now imagine that my system is disordered and that charge localization takes place so that I can only add an additional electron to one of these pockets. If the characteristic scale of these pockets is zeta, and the zeta is small, much smaller than the macroscopic size of my sample, then I'm going to have to apply a substantial amount of backgate voltage before I can add an additional electron to my system. So And as long as adding an additional electron is prevented, the chemical potential is actually going to rise very rapidly. Then when an extra electron can be added, the chemical potential is going to drop very drastically. And this is going to cause a spike in the compressibility, the derivative of this chemical potential. That's impossible. Okay. So I really have to speed up. Okay, if that will be enough. So actually, these spikes in the compressibility is actually where these parallel lines are coming from due to the localization physics. Now, most people that think of localization in the quantum Hall regime have the following single particle picture in mind. They think that localized electrons correspond to electrons that encircle a potential hill or that are trapped in a valley of this disordered potential. And if we think of how a localized state would appear in a density versus magnetic field diagram when localization would really take place like this, then you would easily be able to convince yourself that actually a localized state would have a rather arbitrary shape that depends on the specific details of the disorder. If for a state like this, for instance, if I increase the magnetic field, it wants to maintain constant flux, and so it's going to move up this potential hill. So this one is going to go up, but another one that is stuck in a valley will actually go down and will get filled first. So some will go down, some will go up, and you basically get spaghetti-like, but nothing compared to these nice parallel lines that we saw both in the transconductance measurement as well as in the compressibility experiments. So this is the wrong picture for localized charge localization physics in the quantum Hall regime, even for graphene deposited on top of silicon oxide, which is quite disordered. It should only hold in the very strong disorder limit. The localization physics in the samples that I'm reporting here actually proceeds in the following fashion. We have a bare disorder potential in our system. The electrons, of course, what they would like to do, they would like to flatten this bare disorder potential, and they do so by setting up a spatially dependent density profile. This spatially dependent density profile persists even if I increase my density. It's just going to be exactly the same because my bare disorder potential doesn't change. Now, of course, the degeneracy of my lambda level is limited, and at some point I will reach this maximum degeneracy level, and then what's going to happen is that there are regions where I can no longer compensate the bare disorder potential, and I end up with incompressible regions, and then with these antidots where I can still fill additional electrons. When I fill an electron in there, I'm going to actually get Coulomb blockade physics or charge localization physics. And this is going to produce a spike in the compressibility. So I'm going to get, for every electron that I fill in one of these pockets, I'm going to get a spike in the compressibility. This was at a specific value of the magnetic field. If I repeat the same experiment at a higher value of the magnetic field, of course I'm increasing the degeneracy of my lambda level, but I get the same spatially dependent density profile. And at the same distance from this integer filling, I'm again going to get a lack of screening ability of the electrons in this region. I'm again going to get this charge localization physics. And if I connect these points for different values of the magnetic field, I end up with parallel lines running parallel to the slope of the underlying incompressible ground state of the system. And so now I can understand what actually is happening also in the transconductance. So in the transconductance, if I have a mesoscopic sample, and that's really what I have in this case of graphene, then I'm going to get, when I'm approaching an incompressible quantum Hall state, regions where I can still add additional electrons, and they form a dot network. And as I'm wiggling on my backgate, there will be a backgate voltage where maybe a transport channel through one of these dots gets opened up, because now all of a sudden Coulomb blockade physics no longer holds. I can add an additional discrete unit of charge, and then when my backgate voltage changes, this condition will be turned off again, and so I'm going to get an oscillating current through my system because of this additional channel through this dot network. And this is actually why we also get in this transconductance experiment, despite the fact that it's not a local probe measurement like in the SET experiment, but rather a macroscopic experiment, I get local information from these dots, and so I'm even though my sample is disordered, I'm still able to observe very fragile, incompressible ground states in the system. And the fact that I really have this dot network can be nicely illustrated in graphene, because if I have this situation here that I mentioned in the beginning where I'm at filling factor nu equals 0, there are no extended states, there are not even edge channels anymore. So all that is left for the system to provide conduction from the source to the drain is to go through this dot network. And sure enough, if you do a measurement similar to what you would do in a quantum dot, where you change the drain source voltage as well as some gate voltage that is in the vicinity, you get these diamond-shaped conductance contributions, which is basically just a sign of Coulomb blockade physics. So that's the physics that is occurring in my graphene. And of course, if I'm away from this filling factor, I also get edge channels and things become more complicated. But that's how we can understand this physics. And so I have to move on. So you can basically do the same experiment for bilayer graphene. It's completely analogous. And if you do that, you indeed find a whole zoo of integer and fractional quantum Hall states. You get the symmetries, the SU4 symmetry states, but you also get the broken symmetry states very nicely. And in addition, you can see very nicely here fractional quantum Hall behavior at filling factor 4/3, for instance, and 10/3. And here's the whole set of fractional quantum Hall states that we can observe. I've selected here some. These are the spectra by measuring the correlation function, from which you can even get 1/5 states. And sure enough, that's what I was actually aiming for. You also get even denominator fractional quantum Hall states, both on the electron side as well as the hole side. My time is up. Actually, things in my sample, the last thing I would like to mention is things in my sample are more complicated because of disorder, local disorder, I may have a different transverse electric field in my sample in different regions of the sample. And this may cause a flip of these two levels. And as a result, it might be possible to have filling factor nu equals 1/2, for instance, to be an n equals 0 level as well as an n equals 1 level. This may be one of the reasons actually why I can see both filling factor 1/2 and -1/2 in the system. I should point out that I've oversimplified things quite a bit here in order to make it more pedagogical for the student audience. In reality, things are actually a bit more complicated. And you may wonder, since it's a bilayer, why don't you get this trivial 331 state for a two-layer system, for instance? Actually, there's a number of nice theory papers. I'm not going to choose sites here, but they're all pretty convinced that the physics that we observe is actually genuine even denominator fractional quantum Hall physics related to this 5/2 state in gallium arsenide. So it's this p-wave superconductivity with all its nice consequences like non-abelian excitations and so forth. And some believe that these are manifestations of the traditional Pfaffian, but there was a recent paper by one of the organizers here, Janandra, who actually thinks that this is a manifestation of a 2-to-1 parton state for which I have no intuition at all. It's just a more complex state that also has non-abelian parity. And with that, I would like to finish. Thank
you. So one very quick question is all we have. Sure.
Fractional charge. Can you do something similar here or not?
So actually the best way to extract fractional charge that I'm aware of, the one that is most convincing to me is actually this SET experiment, and which has not been done for the fractional quantum Hall states in graphene. So basically, if you have your SET, here this data that I'm showing here is for a specific location on the graphene. But you could, of course, use the scanning capability and move away. And if you do that, you may find regions where you actually have a very nice isolated antidot. And then if you fill this antidot with charges, then you're going to get these localized states that you are filling. and there's going to be a specific spacing of these states. Now, if you do that at filling factor mu equals 1, you expect that the spacing corresponds to adding a full electron charge, E. If you do, however, at the same location, the same experiment, at filling factor 1/3, then you expect fractional charge. And you should see exactly the same spectra, except that you get for every localized state 3 times as many, because the charge is only 1/3 of the total charge. And that was one of the most convincing experiments to demonstrate fractional charging in gallium arsenide at filling factor 1/3. And I think it would be very nice to be able to do the same experiment in the context of, for instance, bilayer graphene or single layer graphene, but that has not been done. From the transconductance experiment, it's not possible to extract this fractional charge, basically because in this data, you get signals from different pockets. You do not know from which spatial region the particular spike comes from. And so you will always get an overlap of signals from multiple dots, and so it might be very hard to really get that information.
Okay, I think we really